Thank you so much for an opportunity to be back here. I was here a couple of years ago at the MSS conference and thinking, wouldn't it be amazing to come back and talk to you all about our own mission. And here we are 2 weeks from launch and I get a chance to chat about it. So yeah, thank you so much for the opportunity. So I'll go back. So a quick introduction. I'm the founder of Io-1 Technology. We're a small company based in Oxford. And for the last 5 years now, I've been working on a 4U CubeSat to capture data in support of the World Magnetic Model. So we are part of the MagQuest program. So this is an open innovation challenge from the US NGA. And the idea is to support new ways of data collection in support of the World Magnetic Model. So agnostic as the methodology, this could be ground-based systems, it could be space-based systems. And this program started in 2019. We joined it about 6 months later. And that was in phase 2, and we're now at phase 4. So we've gone down from about 200 organizations to a remaining 3 teams who are left, ourselves, University of Colorado, and Spire. And we're all producing CubeSats with very different instruments, very different designs, and we're all launching on the same mission, so all eggs in one basket on Transporter 16. So NGA have offered us not just the funding to do this, but also technical support. So that's included a range of experts and facilities over at NASA Goddard, and they've really helped us kind of to get towards this point. And we are at 15 days, 22 hours, and 49 minutes to launch. Not that I'm counting. So this is Io-1, and you'll see there are a lot of similarities between our mission and the ones we've spoken about so far. We have a scalar magnetometer like Swarm and other satellites. We have 2 star trackers. We have a vector magnetometer, and we have a deployable boom. So we're launching to 590 kilometers. Hopefully, we're going to stay there for about 3 years. We're in the sun-synchronous polar orbit. That's ideal for World Magnetic Model data collection. And we're aiming to achieve an accuracy target of less than 5 nanotesla. But really, the critical difference between what we're doing and these other missions is that we're absolutely tiny. So this is the kind of the family of satellites. I'm sorry, MSS-1 is not on here, but I seem to remember it's about a similar size to Swarm. Got 9 meters for Swarm, getting down to 3 meters for NanoMagSat, and then the absolute baby of the family at just under 1.3 meters is Io-1. So for context, you know, where our payload can almost fit inside one of the star tracker baffles for Swarm. It's that small. So when you get to this point, really everything is miniaturized. So all our instruments, all our components, we're talking kind of thumbnail-sized instruments, and we're really kind of thinking about every single milliwatt of power going into these. So everything is optimized for space and for power consumption and also for cost. Obviously, there are a lot of different challenges. We're trying to shrink everything down to this size. I can't mention them all here. But the 3 ones I think that we've come across that have been most challenging, the first one's magnetic contamination. You know, CubeSats are fundamentally modular. There are a lot of different modular subsystems. Those subsystems are not designed to be particularly magnetically clean, and we don't have a huge amount of choice about what subsystems to use. So it's an important first step is to understand what we're using. The second one is measurement stability. You know, we just don't have access to some of these fantastic instruments that are used in these other missions, these very kind of stable, large, quite power-hungry atomic magnetometers and that kind of thing. And the third is attitude knowledge. There's no sense in having the best vector mag in the world if we don't actually know where that vector mag is pointing. So let's talk about the first one. And the quick win for magnetic contamination is to have a deployable boom. So this is the boom made for us by Oxford Space Systems. If it looks a bit like a spring, it's because it is in some ways. But unlike a spring, when it deploys into a fully rigid state. So one of the first things we did was approach Oxford Space Systems, you know, with this request to transform one of their helical antenna elements into a boom. Before doing this, we really had to understand how long this boom should be. Too long and we lose attitude control of the satellite. Too small and we run into magnetic contamination issues. So really at the very beginning of the process, the first step is to go to our partners, and Clyde Space up in Glasgow are manufacturing the satellite bus for us to try to understand how magnetic these CubeSat subsystems really are. And there's very little data available on this. We went through every single subsystem, from the batteries to the onboard computer and the radio, and we screened it to try to understand what the magnetic moments are. And we were pleasantly surprised. You know, when we put together this synthetic model, we notice actually that, certainly from a static dipole point of view, the disturbances are fairly small. And actually at the location of our scalar mag, we're looking at less than a nanotesla of overall disturbance, which is what we were aiming for. Of course, static disturbance is really only half the battle, maybe it's 25% of the battle. The remaining big challenge, of course, are dynamic disturbances. And we have two instruments on board the satellites that produce those. The first one are reaction wheels. So unlike larger missions like NanoMagSat, which rely on gravity gradient stabilization, I believe, we can't do that. We're simply too small. So we have to rely on active attitude control. So we have reaction wheels, and of course, reaction wheels containing neodymium magnets, the worst offenders for magnetic contamination. So we had a look to see what kind of disturbance these produce. And the fortunate thing is, because these wheels are so tiny, at 23 centimeters, we're looking at about 20 nanotesla peak-to-peak disturbance. And the good news is we're not at 23 centimeters. This boom extends us, so we're more than a meter away from these instruments. And the amount of disturbance from reaction wheels is about 0.1 nanotesla peak-to-peak. And that fits safely within our error budget for this mission. The next one is magnetorquers. Obviously, we need to desaturate those reaction wheels. The way to do that is with torquers. Obviously, at a magnetometer location, those torquers, because they're effectively electromagnets, are going to produce quite a big disturbance. The way to calibrate that out on our mission is that we're turning off the torquers for 100 milliseconds of each 1 second period. And we're attempting to characterize the square wave that is produced. To do that, we have to run our instruments fairly fast. So even though our overall requirement is 1 hertz for this mission, we have to capture data at least 40 hertz in order to fully capture these square waves and basically kind of dynamically calibrate our magnetorquer disturbance every single second. So we've been able to test all these assumptions at NASA Goddard, which has been an amazing opportunity to go to this fantastic facility. If you're familiar with the Goddard Space Flight Center, they have this giant 40-foot Helmholtz coil. It's the one they use to test the Apollo rovers in for magnetic contamination. It is just split over 2 stories. It's an amazing place. And it allows us to produce any magnetic fields in any direction in a very clean environment and really understand everything that's going on with the satellite magnetically. So that has been absolutely invaluable to have their support there. You can see that's our flight model there with the boom extended and then in the stowed state. So instrument stability, that's probably one of the most important things. We have a flux gate magnetometer on board. This is manufactured for us by Bartington Instruments. It wasn't actually our first choice. Originally, we were intending to go with a PNI magnetoinductive sensor, but we realized quite quickly that trying to run it at 40 hertz isn't possible to get the kind of precision we need to really characterize that magnetorquer disturbance. So after spending a few years kind of comparing our various solutions with the kind of flux gate at state of the art and saying, oh, we can do better than this, we can make it smaller or cheaper, actually flux gates are awesome. So we've asked Bartington Instruments to create this flux gate for us, which is a rod core flux gate. And it is incredibly small. There should be a scale here, but this is, it's about 15 millimeters high by 15 by 15. My thumb is at the top there. Absolutely tiny, but it's still a relative instrument. This will still drift over the course of the mission. We need to maintain accuracy over about 5 years. And the way to do that is, of course, with atomic instruments. Now, there really are only a few companies in the world that create atomic magnetometers at that kind of scale. One of them is Twinleaf, based over in the US. We went to them with kind of an impossible proposition. We wanted an atomic magnetometer that consumed less than a watt of power, was around the size of my thumb, and drifted by less than a nanotesla over the course of 4 years. So an extremely challenging brief for them. And a few years later, especially since Twinleaf, they haven't made instruments for space before. So we've teamed up also with Royal Space to test this. And over the course of the last 2 years, we've come up with an instrument you see here. So it's the one kind of wrapped in MLI you see there, just kind of under the circular lid. That's the instrument here. So it's a pulsed-free induction decay magnetometer. We are shining a laser through a very tiny vial of cesium atoms. We're applying a DC magnetic pulse, and we're watching the precession of those atoms with a photodiode. So it gives us a really clean idea of what the magnitude of the magnetic field is in a very, very tiny package. And I believe it will be the smallest atomic magnetometer ever flown in space. So that's going to be an exciting world first, I think. So next up is attitude determination. Like I said before, there's no point having a great vector mag if you don't know which way it's pointing. Originally, our idea actually was to put our star trackers in the body of the satellite here. We had a very complicated idea involving bouncing a laser, this red line here, off the bottom of our payload, off a mirror, very similar to what MagSat did in the 1960s. That way you can determine how the angle of your payload shifts, kind of a laser optical bench, if you will. Of course, that works well in two axes of rotation, but if your payload kind of rotates around the long axis of the spacecraft, you can't pick that up. You can get around it with polarized light and quarter wave plates, and eventually realized we were turning a magnetometry problem into an optical problem, and the whole thing became incredibly complicated, too complicated to pursue. Luckily, we came across ArcSec. So ArcSec produce, again, it's all about kind of the smallest in the world. So they produce the smallest star trackers in the world, these absolutely tiny matchbox-sized instruments that can give you attitude solutions to an accuracy of about 10 arcseconds or less. We need 2 of those, and we were able to work with them for a couple of years to make these non-magnetic. That was the first thing. And also design very, very tiny baffles you can see here, and that's all fit into the kind of gondola we have at the top there. So, the star trackers are non-magnetic, but they're not perfectly non-magnetic. They still contain, currents are flowing through them. We have to separate them from a vector magnetometer in some way. Those of you familiar with Swarm know that the optical bench there is made from some very exotic materials. We also tried to go down the exotic material route. We started off with ceramics, so machinable ceramics like Maycore and Shapel, and attempting to find something that matched the CTE of aluminium. And there's a horrible feeling when you're kind of bolting a ceramic part to an aluminium piece and you hear this very high-pitched dink sound as a crack propagates across your incredibly expensive prototype. So ultimately, we decided to move away from ceramics for that reason, and we moved on to composites. So at the moment, we're using a really interesting peak carbon fiber composite material for this. There's a few reasons for this. One of the reasons is that it's slightly conductive, so it helps us kind of dissipate any static charge buildup. Any charge buildup. And it's also extremely lightweight. It's a bit thermally conductive, so some of the heat from our star trackers is conducted down into the vector mag to keep it at a reasonable temperature. It's very lightweight, it's very rigid, and it matches the CTE of aluminium. We can play around and kind of tune it to match the rest of our components. Okay, so where are we now? This is us taking the satellite all the way to the US. I should mention actually the fourth challenge with CubeSat design for magnetometry is to actually getting it to the launch pad in the first place without upsetting your delicate calibration. So a lot of time sitting with security at Heathrow, trying to persuade them not to put it through an X-ray machine with magnets in the conveyor belt. That slowed us down for a bit. And then trying to get it into an economy seat with a ridiculous number of seat belts to avoid turbulence causing it to hit the ceiling. So we got there, and it is launching in 2 weeks at the LTAN is 2 o'clock in the morning, so it's a really awkward time for us to go out there and watch it. It's the middle of the night. But for you guys, it'll be about 11:30 in the morning on Sunday. So 15 days, 22 hours, and 34 minutes left to launch. Thank you so much.